Hello everyone. Today we will be seeing the effect of source and load resistance on gain of C amplifier. The first step in that is to simulate the circuit without source and load resistance. So this is the circuit without source and load resistance. So just simulate it. Stop. Adjust the scaling so as to get the waveforms. Adjust the cursor so that we get the complete waveforms on the graph. The green waveform indicated is the input waveform, and the red one indicated is the output waveform. As clearly it can be seen that output is inverted version of the input. That means there is a phase shift of 180 degrees. There are two cursors over here, 1 and 2. Take the second cursor to the positive peak of the input and take the first cursor to the negative peak of the input. This will give the peak to peak value of the input and the output waveforms. So where we can observe the peak to peak value, you have a notation T2 minus T1, then there is time values of this, then there is channel A and channel B. Channel A, as can be seen on the CRO, channel A is connected to the output, channel B is connected to the input. So channel A gives the peak value of output waveform and channel B gives for the input waveform. So T2 minus T1, across it, see the value at channel A. It is minus 1.21 volts. So that is the output waveform, and across that T2 minus T1, the value in channel B, that is 9.958 millivolts, that is the input peak to peak value of the input. So gain, as we all know, gain is output upon input. Output from channel A, it is minus 1.121 divided by 9.958 milli. That comes out to be approximately equal to 112.57 minus 112.57. Minus sign indicates a phase shift of 180 degrees. So without the source and load resistance, the gain of the amplifier circuit is minus 112.57. Second, we will see the effect of source resistance, that is RS. So when RS is equal to 100 ohms, the notation given to the gain is AVS. S indicates that is your source resistance. So just replace over here, replace it, your source resistance between input and capacitor. Source resistance comes in series between input and capacitor. Give it a notation, label as our source or our signal. The value is 100 ohms connected to the capacitor as it is in series between input and capacitor. Change the input which is coming from channel B to green color. This completes the circuit. Simulate it and observe the waveforms. Stop it and observe the waveforms. Observation, again it is in the similar manner. We can see that they are inverted to each other, and now we have to see the effect on the gain. For that we need peak to peak values of input and output. So again cursor 2 at the peak value, cursor 1 at the negative peak value. Observe at channel A it is minus 1.079. So AVS over here output is minus 1.079 divided by at channel B it is 9.988 milli. So input is 9.988 milli. This is equal to, this comes out to be 1.079 divided by 9.988 milli comes out to be 108 minus 108.03. So when RS is equal to 100 ohms, the gain is 102.03. Next is RS is equal to 1 kilo ohms. Double click on this, just change the value to 1 kilo ohms. Rest everything is okay, will remain the same. Run it, stop and observe the waveforms. Observation will also be in the similar manner. Cursor 2 to the positive peak and cursor 1 to the negative peak. Over here, if I want to find the gain, that will be equal to, output is 808.475. So 808.475 divided by 9.958 milli. This 808.475 is also milli divided by 9.58 milli. So it comes out to be approximately 80.8. So gain is reduced to 80.8. So you can see as the value of source resistance is increasing, the value of gain is decreasing. Next, let us see for RS is equal to 10K. Just change the value to 10K. Okay. Run. Observe the waveforms. Let's change the scaling so that we can observe it. Observation, cursor to the positive peak, cursor 1 to the negative peak. So the value of AVS is equal to, output voltage is minus 229.968, minus 229.968. Please take care that channel A is connected as your output and channel B is connected as your input. 949 milli. This is equal to 22.9. So the gain has further reduced to 22.9. Next is RS is equal to 100K. So let's change the value to 100k. Over here only we can see that it has reduced to a very large by a very large factor. So the gain over here AVS comes out to be, output is minus 28.133 milli divided by 9.933 milli, which is equal to minus 2.81. So gain is approximately minus 2.81. Looking at these observations, it is very clear that with the increase in the value of source resistance, the gain goes on decreasing because it resists the input which is reaching at the base terminal. So for ideal CE amplifier, the ideal value for good amplification, the ideal value of source resistance should be equal to 0. So this was the effect of source resistance. Now let's see the effect of load resistance. The procedure will be the same. I'll remove the source resistance from here. We don't want to see the effect of source. We just want to see the effect of load resistance. Load resistance is connected in parallel to the output. Adding a resistance. Let's flip it. Change its value. Label it as RL for load resistance. Value initially we will be taking it as 100, the same which we have taken it 100 ohms, which we have taken for the source resistance. Connected in parallel to the output. Okay, so one point is connected to the capacitor, another is connected to ground. Simulate it. Just change the segment color for input so that we can distinguish between input and output waveform. So, adjust it. Now we need to observe the waveforms. Observation will be done in the similar manner. Positive peak and negative peak. Cursors to positive and negative peak because it gives the peak to peak value. AVL. AVL indicates that this is the load resistance we are talking about. So output over here is 42.165 milli. Input is 9.950 milli. So minus 42.165 divided by 9.95. The answer is approximately minus 4.21. So gain is reduced to minus 4.21. This value of minus 4.21 is for RL equal to 100 ohm. So lower the value of load resistance, the gain is very less. Next, let's change the value of load resistance to 1 kilo ohms. So we are changing it to 1K and observe the output waveform. If you can see, there is tremendous increase in the waveform. First, let's adjust it. Let's scale it so that we can see the output waveform. So we can see it on the scale. Take the cursors as told. So the output over here for RL equal to 1K AVL is equal to minus 317.37 milli divided by 9.928 milli, which is equal to minus 31.74. So you can see, as the value of load resistance is increasing, the value of gain is increasing. From minus 4.21, it has increased to minus 31.74. Next, we will see RL is equal to 10K. So AVL is equal to. So let's make this as 10K. Again, we can see that it has increased. Just scale it down. Measure the outputs. Bring the second to the peak value and first to the negative peak value. So T2 minus T1 gives you the peak to peak value. So output is minus 892.277 milli minus 892.277 milli divided by 9.971 milli. It is 892. So this comes out to be 89 minus 89.23. So we can see it has further increased. The last value which we will be taking is RL is equal to 100K. Let's see the gain over here. AVL is equal to, change it to 100K. Observe take the peak to peak values. So it is minus 1088 minus 1.088 volts divided by 9.939 milli. So minus 1.088 divided by 9.939 milli, approximately 109.46. So it comes out to be 109.46. So if we see for Rs equal to 100 ohms, the gain was approximately 108. For RL equal to 100k, the gain is approximately 109, and without the source and load, it is 112.57. So from this, we can conclude that the value of load resistance should be as high as possible to get the maximum gain. So ideally, the value of load resistance should be infinite, but we cannot have that in practical purpose. So let's do the fourth part over here. Let's keep Rs is equal to 100 ohms and RL equal to 100k, and observe what is the output. This output is the output gain. So this is known as AVSL. That means it has both the source and the load resistance. So from the source resistance, it was observed that for Rs equal to 100 ohms, the gain is maximum. Therefore, we are taking Rs equal to 100 ohms. From the effect of load resistance, it was observed that for RL equal to 100k, the gain is maximum. Therefore, we are taking RL equal to 100k. But for an ideal amplifier, the ideal value to have maximum gain, the ideal value is Rs should be equal to 0 and RL should be equal to infinite. So we will be just putting these values over here. So I have RL as 100k. We will be inserting the source resistance also. Let's give it a notation. Its value, we are taking it to be 100 ohms. Its labeling is R signal. Okay. To the connections connected to the input. B terminal, let's change the segment color to green. This is with very less value of source resistance and very high value of load resistance. So approximately the gain should be approximately nearer to the gain without Rs and RL. So it will not be same as without Rs and RL because we are connecting some value, but it should be nearer to that. So 108, 107, something like this. Simulate it. Observe the waveform. So the gain over here comes out to be minus 1.05 divided by 9.963 milli, which is equal to 1.05 divided by 9.963 milli is approximately equal to minus 105.3439. So nearer, approximately we are getting the value in the range of 100. So there is less effect of Rs and RL if Rs value is low and RL value is very, very high. But from this practical, there is a major conclusion which can be drawn is, after observing the waveforms, the major conclusion which can be drawn is, for great amplification or good amplifier, Rs should be equal to 0 and RL should be equal to infinite. The value should be infinite. Thank you.